We're now ready to begin Chapter 5. Chapter 5 is on probability, and Section 5.1 is on probability rules. Putting it together. In Chapter 1, we learned methods for collecting data. In Chapters 2 through 4, we learned how to summarize raw data using tables, graphs, and numbers. As far as the statistical process goes, we've discussed the collecting, organizing, and summarizing parts of the process. Before we begin to analyze data, we introduce probability, which forms the basis of inferential statistics. Why? Well, we can think of probability of an outcome as the likelihood of observing that outcome. If something has a high likelihood of happening, it has a high probability, which is close to 1. If something has a small chance of happening, it has a low probability, which is close to 0. For example, it is unlikely that we would roll 5 straight 6s when rolling a single die 6 separate times. So this result has a low probability. Specifically, the probability equals 0.001286, a very small number. If we were playing a game in which a player threw 5 6s in a row, we would consider that player to be either really lucky or more likely a cheater, because it is such an unusual occurrence. Statisticians use probability in the same way. If something occurs that has a low probability, we investigate to find out what's up. Here in this section, we're going to understand the random processes and the law of large numbers, apply the rule of probabilities, compute and interpret probabilities using empirical method, compute and interpret probabilities using the classical method, and recognize and interpret subjective probabilities. Our first objective is to understand random processes and the law of large numbers. The word random suggests an unpredictable result or outcome. This just means that when we do something, there's no certainty about the outcome. They're equally likely. So, for example, flipping a coin. Yes, we could flip heads. Yes, we could flip tail, but there's no guarantee that we'll flip a head or a tail. They're equally likely, and so they're random possibilities. Simulation is a technique used to recreate a random event. Simulations can be tactile, as in physically or actually flipping a coin and recording the result, or virtual, using a computer to pretend it's flipping a coin. In both instances, the goal of the simulation is to measure how often a certain outcome, such as a head in coin flipping, is observed. To see this idea, suppose we flip a coin 100 times and compute the proportion of heads observed after each toss of the coin. The first flip is tails, so the proportion of heads is 0 heads out of 1 toss, which is equal to 0. The second flip is heads, so the proportion of heads is 1 head out of 2 flips. The third is heads, so the proportion is 2 heads out of 3 flips, and so on. Figure A plots the proportion of heads versus the number of flips. That's the chart down here on the right. Okay. Figure B does the exact same thing. It's just a repeat of the experiment because we want to get multiple data sets that we can compare over time. Notice on figure A, the first flip, we had a proportion of 0, and then we had 1 out of 2, and then we had 2 out of 3, etc. And this is just mathematical in nature, of course, in the beginning, because we're dealing with small numbers in terms of the number of flips. Every flip has a big impact on the graph, but you can see as we get into larger number of flips, the movement is much smaller and likely in a similar direction, as you can see here. We'd expect overall, just in kind of logical sense, that the number of heads over a large number of flips would be equal to 1/2, right? Because there's two possible choices. So if we keep flipping a lot of times, we would assume that over time, eventually we're going to get to about half heads and half tails. And so that's kind of what these graphs are showing, that we're getting closer and closer to 1/2. Even in the part B, we went below 1/2, but then came back up and are centering on 1/2. The graphs and the figures we just looked at, A and B, illustrate a random process. A random process represents scenarios where the outcomes of any particular trial of an experiment is unknown, but the proportion or the relative frequency a particular outcome is observed and approaches a specific value as the number of trials increases. Probability is a measure of the likelihood of a random phenomenon or chance behavior occurring. Probability deals with experiments that yield random short-term results or outcomes, yet reveal longer-term predictability. Like in our experiment before, flipping the coin was a random process. So maybe in the first 5 flips, we get all heads. Well, so those are the outcomes, right? Those are the outcomes. But the probability of throwing a head is something different, okay? So we have random short-term results, like after 5 flips, we had 5 heads, but when we do 100 or more, then you get to the predictability. What is the actual probability that heads will be drawn, which is really 1 out of 2, or half of the times. The long-term proportion in which a certain outcome is observed is the probability of that outcome. That's the long-term proportion. Yeah, we could flip a coin 3 times as we did and saw that we got heads 2 out of 3 of the times, but that doesn't mean that that's the probability. It's when we do a lot of experiments, a lot of these trials of an experiment. A particular trial is each flip of the coin. The experiment is flipping a coin to see how many heads we get, or etc. Okay, so the long-term proportion, when we do a lot of the experiments, then that long-term proportion becomes the probability that that event will occur. The law of large numbers. As the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. That's really just saying the same thing, right? The more flips we do, the closer we're going to get to the probability of 1/2 for 1 out of 2, or 0.5 for flipping a head. Getting an outcome of a head on our flip. The law of large numbers is often confused with a non-existent law. Pay attention here, non-existent law. People use this all the time. This is part of that fake news. Not so much that we report it, but more than our own thinking, especially when we go to Vegas. The law of numbers is often confused with a non-existent law called the law of averages by folks who misunderstand the law of large numbers. Law of averages says something, again, this is a fake law, so it doesn't actually work. The law of averages says something will happen soon or immediately to autocorrect the proportion. So in our last experiment, after we threw the coin 3 times, but we got 2 heads, the law of averages said, hey, it's much more likely now for us to throw tails in the next 2 flips, so that the proportion will average out. This is fake news, because we know every time we flip that coin, on the fourth toss, it is not more likely to land a tail than a head. And that's what the law of averages, and this is why it's fake, it suggests to us. And part of it's like maybe our own stinking thinking, okay, now I'm going to bet on tails because he's already thrown 2 heads. Now it's time to bet on tails because it's much more likely to occur. No, it's not. It's a fake law. The law of large numbers expects the correction to take place over a longer period. And actually, I don't even think the law of large numbers even says that it is exact. Like after, a large number, because you don't know what that number is, you'll get to the actual probability. It just keeps saying you get closer to the probability. So it's a relative answer. In probability, an experiment is any process with uncertain results that can be repeated. In our case, it was flipping a coin. The sample space, this is an important one, denoted with the letter S, uppercase S, of a probability experiment is the collection of all possible outcomes. In our experiment of flipping a coin, we had two possible outcomes, heads or tails. Notice that we put these in the curvy brackets because this is a set of all the possible outcomes. And it's just a list of everything that could happen in your specific experiment. It's identifying all of the possible outcomes. An event is any collection of outcomes from a probability experiment. An event is usually what we're looking for or what we're counting. An event may consist of one outcome or more than one outcome. So our event was, what's the probability of flipping a head? Okay. We will denote ends with one outcome, sometimes called simple events, with a lowercase e sub 1. In general, events are denoted using capital letters such as E. So let's look at a little example here. Probability experiment consists of rolling a single fair die. If you look at the bottom here, a fair die is one in which each possible outcome is equally likely. For example, rolling a 2 is just as likely as rolling a 5. We contrast this with a loaded die, if you may have heard that term before, in which a certain outcome is more likely. These are things that are cheating, right? So it's more likely that you'll roll a 2, so you would bet on a 2. Okay. So part A, identify the outcomes of the probability experiment. Our experiment is to roll this 6-sided die. What are all the possible outcomes that we could get? Well, they're each side of the die, right? So they're the numbers 1, 2, 3, 4, 5, or 6. Okay, those are the different outcomes of each trial. So I roll the first time, I get a 1. I roll the 15th time, I get a 3, etc. Each experiment, each trial of the experiment gives me one outcome. Determine the sample space. Well, the sample space is all of the possible outcomes, so it's the set of 1, 2, 3, 4, 5, and 6. And notice we listed them there. So defining an event tells us what the outcomes are, and then and what the sample space is. So define the event E, which is to roll an even number. So event E is rolling a single fair die and getting an even number. And so the even numbers that are on a fair die, when we look back at the sample space for just rolling a die, we can see that we have 2, 4, and 6. So our event E has the outcomes 2, 4, and 6 in its sample space. Our second objective is to apply the rules of probability. The first rule of probability says that the probability of any event, denoted P of E, P left parenthesis, E right parenthesis, must be between 0 and 1. That is, 0 is less than or equal to P of E, which is less than or equal to 1. An event that has a probability of 1, you might think of this as a 100%. If something is 100% likely to happen, it is a certain event, and so its probability is certain, its probability is 1. An event that has a probability of 0 is an impossible event, and it will never occur. So for example, if I said, what's the probability of rolling a fair die and getting a 1, 2, 3, 4, 5, or 6? Well, the probability is 1 because those are the numbers, those are all of the numbers that are on a fair die. If I said, what is the probability of rolling a fair die and with an outcome of 7, well, that probability is 0 because there's not a 7 on the die, and that's an impossible event versus the certain event of rolling a 1 through 6. The second rule of probability states the sum of the probabilities of all outcomes must equal 1. So if the sample space has these members in it, event sub 1, event sub 2, E sub n, etc., these outcomes, then the probability of E sub 1 plus the probability of E sub 2, so on until we get to E sub n, has to equal to 1. In the case of our die experiment, we would say the probability of rolling a 1 plus the probability of rolling a 2 plus the probability of rolling a 3 plus the probability of rolling a 4 plus the probability of rolling a 5 plus the probability of rolling a 6 would equal 1. The sum of the probabilities of all individual outcomes must equal 1. A probability model lists the possible outcomes of a probability experiment and each outcome's probability. A probability model must satisfy rules 1 and 2 of the probabilities that we just went through. So let's look at an example of a probability model. The color of a plain M&M chocolate candy can be brown, yellow, red, blue, orange, or green. Suppose a candy is randomly selected from a bag. Table 1 shows each color and the probability of drawing that color. For example, the probability of drawing a brown M&M is 0.13. Of drawing a blue one is 0.24. This means not likely that there are more blue. They create more blue M&Ms than they do brown, just overall. Verify that this is a probability model. To verify that we have a probability model, remember the models have to meet the 2 rules. So we just have to show that rules 1 and 2 are satisfied. The first is that every probability is between 0 and 1, and we can see that they're all greater than 0 and less than 1. So rule 1 is satisfied. The second rule says that all of the individual probabilities together must add up to 1. So we add these 1, 2, 3, 4, 5, 6 different color probabilities, and we do get 1. So rule 2 is also satisfied, and the table is an example of a probability model. So our lecture today is about 45 minutes. So again, this is a good time to take a break. We're past halfway through the slides, but about halfway through the time. I'll leave you with a little quote here. Integrity is telling myself the truth, and honesty is telling the truth to other people. I always like the definition of integrity, that integrity is when your actions meet your words, that what you say you're going to do or what you say you believe in is in agreement with what you actually do. Okay? And a big part of this statistics is about finding data so that we can validate or give a confidence level about how true or how real or how valid information is or opinions are. And this is something, in my opinion, very clearly stating it's my opinion, that is what's really lacking in our culture right now. And part of that is about technology and social media, about anyone being able to say anything. The other thing about that, though, is that statistics leads to it. It's always been a history of that numbers can tell a story, and numbers can tell opposite stories depending upon how people use them. So, using your data correctly and with integrity to me is important. Now take a break, get a coffee, take a walk, and then come back refreshed and finish up the lecture. Our next objective is to compute and interpret probabilities using the empirical method. The probability of an event E is approximately the number of times E is observed divided by the number of repetitions of the experiments. So we can see here this is the frequency of E, how many times do we observe E, and then how many total experiments there were. This is what we looked at in chapter 2 or 3, sorry I can't remember, and we called the relative frequency of E. So this is something we're already doing, so probability, we're kind of mapping into that already with our relative frequency that we did. I think that was chapter 3 when we did the graphing. Using relative frequencies to approximate probabilities. Here's an example. An insurance agent currently insures 182 teenage drivers ages 16 to 19. Last year, 24 of the teenagers had to file a claim on their auto policy. Based on these results, the probability that a teenager will file a claim on his or her auto policy in a given year is the 24 that filed last year, the frequency of this event, E, teenagers filing a claim, divided by the total number of observations, and we had 182. So we have 24 divided by 182, so we get an approximate probability of 0.132 or 13.2%. So the way we would read this is for every 100 insured teenage drivers, we expect about 13. Why do we say about 13? Because it's an approximation. We expect about 13 to have a claim on their auto policy. How do we build a probability model from survey data? The data in Table 2 represents the results of a survey in which 200 people were asked their means of travel to work. Use the survey data to build a probability model for means of travel to work. So remember, what we're trying to do is to figure out, for probabilities, we take the frequency of a response, for example, driving alone is 153, divided by the total number of observations, or in this case, the total number of answered surveys. Well, we have that answer here, but if we didn't have that given to us, we would simply add all these numbers, which we did again in the relative frequency table that we built in chapter 3. There are 200 responses noted. The individuals can be thought of as trials of the probability experiment. So the relative frequency for driving alone is 153 divided by 200. This gives us 0.765, which is a pretty large piece, which we can see it is the most common answer. And then we just simply compute the rest of the outcomes similarly. For carpooling, we take 22 divided by 200. For public transportation, 10 divided by 200, etc. And so you see the results here in the table to our right, which is in, the entries are in yellow. Okay, so we've built a probability model for the data that we were given in this survey, in this frequency chart, frequency distribution chart. Question B asks us to estimate the probability that a randomly selected individual carpools to work. Okay. Well, we don't. Now, why does it say estimate? Okay. When we look at the table, we can say that the probability is 0.11, but remember this is an estimated probability, and so that's why the question has to say estimate the probability. It can't say what is the probability. If they said what is it, then we'd have to use the word approximately, etc. Okay, so we estimate the probability to be 0.11, and again we think of this as a percent, 11%, or if we were to survey 100 individuals, we would expect about 11 to carpool to work. So the last question is, would it be unusual to randomly select an individual who walks to work? It's a weird way of saying this, but remember these are those outliers, if you will, that are unlikely to happen. And so we're looking for things with a very low probability. As far as walking to work, we have a approximate probability of 0.025. So this is 2.5%. It's pretty low. The probability is approximately 0.025. So that means 2.5 people out of every 100 surveyed. I know it's not politically correct to say half a person. 2.5 people would respond that they walk to work. So if we multiply those by 10, we say if we serve 1,000 individuals, we would expect about 25 to walk to work. Therefore, it is unusual. It's not impossible, but it is unusual to randomly choose a person who walks to work just because the percentage is so low. Just because the percentage is so low. Our next objective is to compute and interpret probabilities using the classical method. What we just did was the empirical method using frequencies and relative frequencies to figure out an approximate percentage. Here we're going to use the classical statistical method. Probabilities using the classical method. Before we can use the classical method, we have to realize that we can only use this method for computing probabilities if all of the outcomes are equally likely to occur. So in the last survey example, we really couldn't use the classical method, okay? And that's why when you see the surveys on TV, you see this likelihood of error or range of error plus or minus 2% points or something. Okay? An experiment is said to have equally likely outcomes when each simple event has the same probability of occurring. For example, flipping a coin. Heads has an equally likely outcome or an equal chance of happening as tails does, and vice versa. Okay? Computing probability using the classical method. If an experiment has equally likely outcomes, then the probability that an event can occur is the number of outcomes of the event E divided by the number of total possible outcomes. So notice here now we have an equal sign. So we can calculate the actual probability of flipping a coin because flipping a coin has equally likely outcomes. And in this case, we take the number of outcomes that we're looking for example, flipping a head, divided by the number of total possible outcomes. Well, remember, this is what we call the sample space, so the number of members in the sample space. So if we're talking about the number of the probability of flipping of the outcome being head, well, there's only one outcome, it's head, and there's only two possibilities, head or tail. So the actual probability of flipping a coin and getting a head is 1/2 or 0.5. So let's look at an example now for computing the probabilities using the classical method. A pair of fair die is rolled. The first thing we want to do is compute the probability of rolling is 7. Remember the classical method, the formula for that is the number of outcomes that equal the event, in this case rolling a sum of 7, divided by the number of total possible outcomes. So if we're rolling 2 fair die, that's 6-sided cubes that have an equal likelihood of landing on any of the 6 numbers 1 through 6. But notice we have a pair of them. So drawing a diagram or a table with all the options is sometimes the best way to do this because it'll also help us figure out how many options add up to 7. Here we have a diagram that actually literally shows the 2 die. The first row shows the first die with a 1, and then the second die with all 6 options. So notice that when the first die is a 1, we have 6 possible outcomes with that second die being 1, 2, 3, 4, 5, 6. The second row, the second die is 1, and then of course we get 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, which again is another 6 possible outcomes for there. When we go through all the different options, we can see we have 36 possible outcomes. That means the sample space has 36 members in it, which is important to our calculation. While this table is nice and you can really visually see it, I tend to use a multiplication table type process where I would write the options for the first die across the top, 1, 2, 3, 4, 5, 6. Write the option and possible outcomes for the second die along the column here, this first column, so for the titles of the rows, 1, 2, 3, 4, 5, 6. And then what you have in each block or cell is really what you think of as a multiplication table. So 1 times 1 is 1, 1. 1 times 2 is 1, 2. 1 times 3 is 1, 3, etc. We could do any of these here. So in the middle, we have 3 times 3, etc. And I'm saying times, but really I'm just saying so you could see the members there. That's what we do in a multiplication table, is multiply the column heading and the row heading to get that cell member. I don't know why that's easier, maybe just because we're more familiar with a multiplication table. Also, who's going to write all these little dots out, etc. This would take a lot of time. So you could build this without being so pretty and fancy, just by thinking of it as a multiplication table. And so like the last member is 6 by 6. All right. So when we have this, we know that the number of members in the sample space is 36. Now we have to figure out how many outcomes have a 7. So what we're looking for is the sum of the two die is a 7. And we can see the first one is here, 1, 6. And then, of course, it goes down to 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So it's actually the whole upward diagonal. And that's often the case with some of these multiplication tables. They tend to happen in patterns. So we can see that there are 6 options, 1, 6, 2, 5, 3, 4, etc., that roll a 7. So there are 6 possible outcomes adding to a 7. That means n of e equals 6. Out of 36 possible outcomes, which is n of s equals 36. So the probability equals, remember this classical method is the probability, 6 out of 36. It's not an approximation, so we get 0.1667. Now we're ready to do the second piece, which is to compute the probability of rolling snake eyes. That is, snake eyes is this one up here where it's 1 and 1. Well, there's only one outcome that is snake eyes, or 2, and out of 36 items, a possibility. So 1 out of 36 equals 0.277. That calculation is wrong. One out of 36 is 0.0277. Okay? Or really 0.0278. Comment on the likelihood of rolling a 7 versus rolling a 2. Well, we can see that rolling a 7 is 6 times more likely, since there are 6 times as many outcomes. In other words, in 36 rolls of the dice, we expect to observe about 6 7s and only 1 2. And what we mean by 2 is a sum of 2. So now let's look at our final example, computing probabilities using equally likely outcomes. Sophia has 3 tickets to a concert, but Yolanda, Michael, Kevin, and Marissa all want to go to the concert with her. To be fair, Sophia randomly selects the 2 people who can go with her. Determine the sample space of the experiments. In other words, list all possible simple random samples of size n equals 2. Okay. Again, here we need to figure out what are the possible outcomes. And again, you could do a table here, but it's a little bit confusing. You can't do the multiplication table because if we select Yolanda and Michael, if we reverse the order, Michael and Yolanda, that's really the same 2 people going. So you can't double count. Like in the die, a 2-3 was technically different than a 3-2 because you were rolling 2 die, and that's technically another possibility. There were 36 possible outcomes here. But since in this case, Yolanda and Michael going to the concert is the same as Michael and Yolanda, we have to do a little bit different method, and that is we can't count them. Order is important. Order is not important because a reverse order gives you the same one, whereas before order was important because a different order indicated a different possible outcome. Okay, so all we have to do is go through here and start with each name: Yolanda Michael, Yolanda Kevin, Yolanda Marissa. And then we have Michael, Kevin, Michael, Marissa. And then we have Kevin, Marissa. So we can see all of these, and they're not that very difficult because we just had to kind of walk through. Yolanda, Michael, Yolanda, Kevin, Yolanda, Marissa, then Michael, Kevin, Michael, Marissa, and then Kevin, Marissa. This handles all of the combinations. You'll see that Marissa is with Kevin, Marissa is with Michael, and Marissa is with Yolanda. So you do see all the different combinations there. So in this case, our sample space is these 6 entries, and the number of responses of possible outcomes is equal to 6. Compute the probability of Michael and Kevin attending the concert. Well, there's only one option of Michael and Kevin attending the concert, so there's 1 out of 6 possibilities. So the probability is 1 out of 6, the number of outcomes that meet the event, Michael and Kevin, divided by the total number of possible outcomes. Compute the probability of the event that Marissa attends the concert. Now in this case, this is just asking us what's the likelihood that Marissa will get to go. So notice there are Marissa, Marissa, Marissa. There are 3 out of the 6 outcomes that include Marissa. So in this case, the number of outcomes for the event, Marissa attends the concert, is 3. And so our probability that Marissa goes is 3 out of 6, or 0.5, which would be the same for all 4 candidates, right? They each have a 50-50 shot of going to the concert. And this is how your book interprets it. I wouldn't interpret it this way, but it says if we conducted the experiment 1,000 times, about 500 of the experiments would include Marissa. So they're putting it in terms of an experimental observation, which is okay, but this is really a 50-50. So then no matter how many experiments we conduct, we would expect that Marissa or any of the people would be included about half the time. Now the reason that they're doing 1,000 times is really the law of large numbers, right? So we expect that over time, that the probability will equal out, or our observation of the probability, which is not the exact probability, will even out. And so again, I understand why they're interpreting it this way, and you may see that in your homework. You know, the probability really just says that, everyone has a 50-50 shot of getting it. But if we're talking about the probability in light of the law of large numbers, then we would, pick a large number of observations and then conclude that, about half of them should include Marissa in this case, or a candidate. I lied. There is one more example. Comparing the classical method and the empirical method. Suppose that a survey asked 500 families with 3 children to disclose the gender of their children and found that 180 of the families had 2 boys and 1 girl. Okay? Estimate the probability of having 2 boys and 1 girl in a 3-child family using the empirical method. Well, this is really simple because remember, what we're doing with the empirical method is we're just using the observations. How many people did we observe total? In this case, it was 500 families. And how many of those observations met our event that we're looking for, which was 2 boys and 1 girl. So in this case, the event has 180 observations. The sample space, or the total number of observations, was 500. So we just make that calculation. Remember that the empirical method calculation of a probability is an approximation. And it's also, you can think of the probability using the empirical method, and this BB stands for 2 boys, boy, boy, is approximately equal. It is equal to the relative frequency. The probability is approximately equal to the relative frequency, which is how we calculate the approximation. The number of times the event observation occurs over the total number of observations. So we get a probability of approximately 0.36. Using the same example, compute and interpret the probability of having 2 boys and 1 girl in a 3-child family using the classical method, assuming boys and girls are equally likely. This is a much more difficult case of creating the sample space, right? All the possible outcomes. So the idea here, and you would do this even if you were flipping a coin 3 times, is think about each of the children, the first child, the second child, the third child, and what the options are. Okay, and here we can build something called a tree chart. So for the first child, we have the option of a boy or a girl. Duh. The second child, we have that same option, boy or girl. But notice, if the first child was a boy, then we have that option, boy, girl, for the second child. If the first child was a girl, we have that same option, boy, girl, for the second child. And then the third child, we have that same boy, girl option. But notice now, what's happening is we have these different kind of organizations of families. So this first one is boy, boy, boy. And then second one is boy, boy, girl. Boy, girl, boy. Boy, girl, girl. Girl, boy, boy. Girl, boy, girl. Girl, girl, boy, and girl, girl, girl. So when we count these, we can see that we have 8 different options, possible outcomes based upon each child. This is similar to the last one, although you might say, well, wait, isn't boy, boy, girl really the same thing as boy, girl, boy in terms of the event, 2 boys and 1 girl? It is in terms of the event, but there are different families that have different options of how those children come out. And so these are all the possible options for different families. So we have to consider each case. And so in this case, order does matter, that we don't consider BBG, boy, boy, girl, the same as boy, girl, boy, because it's a different kind of alignment in the family. And each child has a 50-50 shot of being a boy or a girl. And so when we stack them, we get different options based upon the order. So here are all the possibilities, all 8 possibilities, boy, 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 girl. And here it's much easier to see, and so we can calculate the probability. So here we can see that the sample space has 8 members, and we're looking for specific outcomes that have 2 boys and 1 girl. So we can see that there's 1, boy, boy, girl, 2, boy, girl, boy, 3, girl, boy, boy, and I think that's it from what I see. So the number of outcomes, the number of different possibilities or different arrangements of 2 boys and 1 girl is 3. The sample space is 8, so our probability equals, remember that when we use the classical method, we're calculating an actual probability. So the probability equals, not is approximate, to 3 over 8, which is 0.375. And again, the interpretation here is if we conducted 1,000 observations, we would expect 375 families with 2 boys and a girl in them. Our last objective is to recognize and interpret subjective probabilities. A subjective probability of an outcome is a probability obtained on the basis of personal judgment, not data. A subjective probability of an outcome is a probability obtained on the basis of personal judgment, not data. So it's not really an official probability, okay? For an example, an economist predicting there is a 20% chance of recession next year would be a subjective probability. Okay, so this isn't a real probability. And when they say things like this, it makes people think that, that there is a greater or lesser likelihood of an event occurring. But we have to remember that this is an opinion, not a statistical data fact. And, to me, this is where a lot of our fake news comes in, because you will see a lot, I bet you on every newscast you see multiple things that are suggested as news, which are really just opinions stated by someone. And there's an old cliche about opinions, so it's a little inappropriate to share here, but it's about everyone having one and no one thinking theirs is bad or stinks. Anyway, so be careful about subjective probability. When people are giving you a prediction and making it look like a likelihood or probability, a 20% likelihood of something occurring, ask them what they're basing that on. Is it some form of data? And they're all going to say it's some form of data, but you want to know what that data is. so that you can, temper your judgment about the validity or the confidence you have in the validity of that statement. And remember, that's part of statistics, is how confident are you in your results? That when you report results, you also report, we learned this in chapter 1, a confidence level about how you feel about the results you obtained.